Okay, so in this video we're going to take a look at a different kind of complexity. We're checking out space complexity. Now, so far we've only looked at time complexity, how to analyze the relation between the input and the runtime of an algorithm as the input increases. In today's video, we're going to focus mainly on space complexity, which is basically finding how much additional memory do we need to consume for our algorithm to actually execute. Now remember, and this is something you probably already expect, when you're analyzing space complexity, you only care about the space the algorithm takes. You do not care about the space taken by the input or whatever, only the space taken by our algorithm. To start things off, let's start with an example. So here we got a simple function called SumUp2, takes in an array, and we're expected to return the sum of the elements in that array. Now, what do you think is the space complexity for this function? Well, let's count the number of variables. So here we got these two variables, the sum, which is initially at 0, and n, the length of the array. After that, in our loop, the I, which is the loop's counter, get assigned n times. But it's still a single variable. Doesn't matter how many times an operation was done on it. The time complexity concern is the number of operations that was done on it. But we're concerning ourselves with the space complexity only. So this is actually big O of 1. This is constant because we don't have any extra memory saved that has a relationship with n in any way. Let's see another example. This time we have a function called getArray_up_to or getArray_up_to, which takes in some number n as input, and now all this function does is that it loops for n times and then appends the index of the loop to an array that we created before the start of the loop. So what is the space complexity for this case? Well, the algorithm is actually linear. It's big O of n. But how? Why? Well, our array size have a direct linear relationship with the input n. If n is 1, that will make the array have 1 element. If it's 100, the array will contain 100 elements. So due to this linear relationship, we can say that this algorithm have a complexity of big O of n in terms of space complexity. Now, let's skim through the space complexities of some popular data structures. Let's start with hash tables, also known as dictionaries or hash maps, or simply just maps. They have a space complexity of big O of n. They are linear. That's because the number of slots needed to be saved in the hash map increases linearly with the value of n. If we have n elements, that means that we want to have n elements allocated in the memory to actually store them. Same thing for stacks, queues, strings, and arrays. All of these data structures have a linear space complexity because the number of elements needed to be allocated in the memory have a direct linear relationship with our input n. But say we were given 2 inputs and an m, and we're asked to create a 2D array that has n rows and m columns, for example. Well, in that case, the number of elements needed to be allocated in the memory will be n multiplied by m. So we can say that 2D arrays have space complexities of big O of n multiplied by m, where n and m represent the row and column sizes. And that's it. In the next video, we're talking about logarithms. See you then.